All right, so welcome to the second part of the Schubert seminar. Is Tommaso Botta telling us about 3D mirror symmetry and bow varieties from curve counts to Schubert calculus. Please take it away,
Yeah,
Tommaso.
thanks once again. So yeah, in the unrecorded part, I was just pointing out that I realized that I forgot to make this notation explicit. These are simply cupocalmers. So I'll just give them by this definition. Anyway, so okay, so far we've introduced some kind of enumerative problem, the problem of counting P1s in the quasimap sense to a queer variety, but no relation to with mirror symmetry has been made. So let's try to do it now. So the relation with mirror symmetry or symplectic duality, so to speak, comes, I mean, can be understood in terms of the of this difference equation problem. Okay, so in general, from the very definition, one can notice that uh, the vertex functions are not really symmetric in the two variables, in the sense that they will be in general holomorphic in a in a neighborhood of q equals 0 because they are really expansions in modes with respect to q. But in general will be wholly meromorphic in these. One can really see it from, for instance, these denominators. Okay, so they're kind of asymmetric in the two variables. So one can ask himself how to, if the same set of difference equations has a different basis of solutions that where the rows of the A's and the Q's is swapped. Okay, and so in general, any if we have like two different set of solutions, let's say Q solutions regular in the Q and A solutions regular in the A's, then the two solutions are supposed to be related by some kind of matrix. Uh, and this matrix, since it's a matrix relating different bases of solutions of a system of difference equations, has to be periodic with respect to the shift of the difference equations. So it has to be some sort of elliptic function, or let's say matrix of elliptic functions. So, and what enumerative mirror symmetry says is that the A solutions, so the solutions that are regular in the A, are supposed to be taught as the curve counts to the dual variety. Okay, so we start with our target, our Higgs branch, so to speak. We count curves to the Higgs branch. We have some power density expansion in the formal variable, and this formal variable. I mean, with respect to this formal variable, the expression will be regular, and on the dual side, they're all the but it will be just meromorphic in the we have poles in the equivariant parameters, and but on the dual side, working on the dual side, we can instead obtain solutions that will be well, the rows of A and Q are swapped. Okay, so this matrix, which solves the problem of moving from one set of solution to the opposite set of solution, may be called like the pole subtraction matrix, because like removes poles in one variable and adds poles in the other one, can be characterized without reference to mirror symmetry, uh, and that this is what has been done in the important work of Aganagic and Okounkov, where this post-subtractive matrix is characterized as the elliptic stable envelope. So the elliptic stable envelope is a distinguished class in the equivariant elliptic homology of the Nakajima queer variety tensored with its fixed locus. So it has really can be thought as a correspondence from the fixed locus of the queer variety to the queer variety itself, and it's a correspondence in elliptic homology. Sadly, there's no time to discuss the details of this construction, but you can really think of this as some kind of upgrade to elliptic homology of some kind of Lagrangian correspondence in singular cohomology or equivalent theory. And the equivariance is really the one with respect to the original torus A times C star H bar, but we also need to plug in the so-called Kähler torus, which really records the parameters entering in the curve count. And although this torus acts trivially on the queer variety, it will enter in a non-trivial way in the definition of the stable envelope. And actually, it is an important conceptual point. But as I said, one can really talk these are Lagrangian correspondences, and they are uniquely characterized by a list of axioms, but they are uniquely characterized as soon as one fixes something called a chamber which is a connected component in a wall chamber arrangement in the co-character lattice of the torus A. So A is the torus of symplectomorphism symplectomorphisms of my queer variety. Okay, so for whenever X is the cotangent bundle of a partial Flag variety, this is something that can be obtained in type A. Okay, the stable envelopes, or more precisely, the restriction of the stable envelopes to each of the connected components in here, is really an elliptic version of of Schubert classes, or more precisely, of some linear combination of Schubert classes. And the chamber dependence is really some kind of key aspect of the theory, because so one can consider transition matrices obtained as composition of Lagrangian correspondences for stable envelopes coming from different chambers. And for the appropriate choices, I don't want to enter in the details, but crossing walls in a different way in the wall chamber arrangement, one can really notice that elliptic stable envelopes reconstruct solution of the dynamically Baxter equation, which was, I guess, at least in the mathematics literature defined by Felder a long time ago. And essentially, they provide these matrices, the elliptic R matrices, the solution of the dynamically Baxter equation recover braidings for elliptic quantum groups. So this is some kind of side perspective on this whole business, but still an important one, I'd say. Anyway, so in the case of the cotangent bundle of the projective space, formulas are known. And so I'm showing you this formula not because I'm expecting you to focus on the details. All I want to convey is somehow the idea of how to think of this stuff. So very concretely, abstractly, we have this Lagrangian correspondence in elliptic homology. Concretely, if you localize everything to fixed point, assuming that fixed points are isolated, that can be done very explicitly. And these are really, the elliptic stable envelope can be thought as some kind of more or less crazy, depending on the target variety, more product of theta functions. Theta functions, Jacobi theta function. So function, Jacobi theta function, which are sections of distinguished line bundles on the, using the language of elliptic homology, one would say section of line bundles on the universal line bundle on the elliptic homology of the point, something like that. And so how to put all this together in the context of mirror symmetry? Well, let's formulate it as the following conjecture by Aganagic and Okounkov. So whenever everything is well defined, so whenever all the curve counts are defined, whenever the stable envelopes are defined, then the following two statements hold. The first one is that the counts on the dual sides are related and are related by this pulse abstraction matrix, which is realized as an elliptic stable envelope. Okay. And the second statement is that the stable envelopes themselves of dual varieties, X and X dual, are one of the inverse of the other. And somehow you see that somehow the second statement makes the first one symmetric because I can just move the stable envelope on the other side. And both these equalities have to be understood after the appropriate identification of the parameters. So you see that somehow the torus equivalent parameters A on one side are identified with the parameters of the generating series on the dual side, and vice versa. And that's why somehow regular functions in one variable become uh, mm, um, I mean, well, what I want to say, well, let's just say this is the way the parameters have to be related. Um, so let's say a few words about the history of this conjecture. So first evidence is in the case of hypertoric varieties, which can be thought as a kind of abelian version of of queer variety quotient. Uh, in the case of the cotangent bundle of the full flag variety in type A, X and its dual are the same. This doesn't mean that mirror symmetry is easy in this case. There's still a extremely non-trivial identification. And this is essentially because the bases of solutions of the difference equation in the two variables are very different. Okay. But yet it is shown in the article by Smirnov, Rimanyi, Varchenko, and Zhu, and of Dinkins, that mirror symmetry holds, both in the case of full flag variety and also in the case of the cotangent bundle of the Grassmannian, which is not self-dual, and yet uh, whose dual is still a queer variety. This is another technical but important point, and actually leads to one of the main reasons why dealing with such mirror symmetry statement, the one involved in this conjecture, is not easy. It's not easy because so you see that there's this condition whenever everything is well defined. So in general, as soon as we move away from the realm of queer variety and we look at general Coulomb branches, we may start and deal with things that are non-smooth and they cannot be, well, at least we don't know how to resolve. So because of that, the curve counts are not defined, the stable envelopes are not defined, and somehow all the machinery ceases to exist. Okay. However, not everything is lost, and somehow that's what this talk is probably about, besides being an overview on the subject. And so let me somehow um, share with you the following theorem. It is so very compactly, it says that the conjecture 2 holds for arbitrary. So the second conjecture, the one about the stable envelopes, mirror symmetry behavior of stable envelopes, holds for arbitrary Bow varieties, and this is joint work with Rimanyi. And the conjecture, and the second part of the theorem says that also conjecture 1, so the one relating the vertex function, holds for arbitrary Bow varieties. And this is joint work with Hunter Dinkins. So of course, if I state it in this way, I'm not telling you much because I'm not telling you what a Bow variety is. So let's look at that. So to understand somehow what this theorem is saying and what is the actual problem of discussing mirror symmetry in a certain level of generality, we somehow we need to look at the geometry of the dual as I was hitting at before. So in general, if I'm given a queer variety, so because of the GAT presentation, the queer variety will have a singular version, just the quotient with respect to the trivial stability condition, but it will also come with a resolution. Okay, so this is like the case of TP1. We are blowing up a point, and in general, as soon as I look at the Coulomb branch, to be honest, and of course I'm supposed to be honest here, There's no resolution in general. There's no GAT presentation. All it's known, I mean, it's a lot, but it's not all we want, is that there's a meaningful and precise mathematical description of the affine and singular version of the Coulomb branch. And this is due to Breverman, Finkelberg, and Nakajima. So this definition is great for many, many purposes, but for the sake of studying counts, it's complicated. There's no meaningful, I think, way of counting curves in these singular varieties. Um, so, and in particular, there's no, even in the case when, even if there's a resolution, for instance, in type ADE, slicing of Grassmannians can be used to produce resolutions, at least under some amount of technical condition. But still, that's not GAT. Those resolutions have not GAT presentation, and so defining the vertex function is not an easy problem, or let's say the equivalent of a vertex function in that context. So, what is the natural level of generality where we can at least formulate the mirror symmetry problem? Well, I'd say this is the case of is affine type A in principle. Because in this case, thanks to the work of Nakajima and Takayama, we know that not only we have the queer variety, but so which is GIT, but also the dual admits a GIT presentation. And somehow I think that my understanding, well, is that this comes from something known as S-duality, which essentially says that these 3D theories with supersymmetry n equal 4 essentially have a gauge theoretic duality known as S-duality, and has one of the defining properties is that it swaps Higgs and Coulomb branches on dual side. And usually Higgs branches on the Coulomb branches do admit GAT presentation. And so if one understands symplectic duality, can transfer the GAT presentation from one side to the other. And I think that's more or less what motivates the work of Nakajima and Takayama. But the upshot is that, as I was saying, in type A, we do have all the tools, at least all the presentations we need to formulate the problem. And so the varieties we get are known as Bow varieties. They are those filling this picture over here. So in type A, all these spaces can be realized as Bow varieties. So in particular, we have all the data and the structure required to define mirror symmetry. So Bow varieties comprehend both type A queer varieties and their duals, as I was saying. And so I will not enter any details, but they also admit, and this is another important point, they also admit some kind of quiver description. It's slightly more involved than the one for queer varieties, or at least like it's a different flavor of it. The presentation has a very beautiful combinatorial description of what, in terms of what is sometimes called a bow diagram, which has to do with some of the string theoretic and gauge theoretic interpretation of these quiver gauge theories. At a very lower level, a much lower level, they can be taught as a kind of a combinatorial gadget consisting of 3 types of horizontal lines together with a number of dimensions. And the idea is that the shape of the diagram allows you to construct some quiver. This dimension vector D is the analog, it's not exactly the same thing, but it's the analog of the dimension vectors V and W for a quiver variety. And it is still true that I can realize the Bow variety as some GAT quotient. And now the GAT quotient is still the GAT quotient of a representation scheme. The only thing is that it's not the representation scheme of the path algebra of the quiver, but rather of some kind of appropriate quotient. And somehow the morale of the story, the idea is that for queer varieties, I'm simply consider some symmetric quiver. It's whose space of representation is a cotangent bundle, so it is symplectic, and I just take the symplectic reduction. For a bow variety, in general, the space of representation of the quiver is not symplectic, it's Poisson, so I need to pick some kind of symplectic slice. And picking the symplectic slice has to do with taking these relations. So I'm not telling a lot about bow varieties, but what I think that what the message I'm trying to convey here is that they provide the geometry and the combinatorics to study Higgs and Coulomb branches in type A. And in particular, they provide they give us all we need to tackle mirror symmetry. And so the previous theorem I displayed over there, the one in joint work with Rimanyi and Dinkins, tells that in type A we can prove all the whole mirror symmetry conjecture. Now, to be precise, when I say type A here, I really mean finite type A. So the affine version is still to be fully understood. But yeah, so the theorem, so we have a theorem in type A, and so we can relate the curve counts of any quiver gauge theory in finite type A. And so maybe let's also point out that the combinatorics of the bow variety let us have a very efficient combinatorial way of describing the duals. So in principle, in principle, understanding the duality maybe, well, it is fine, but it's not. Combinatorial gadgets are usually important in this business, and both varieties provide a very efficient combinatorial very efficient combinatorial tools. And in particular, if I'm given any variety X that admits this bow presentation, then its dual is simply obtained by reversing these lines, which are known respectively as D3 branes. Sorry, D5 branes and NS5 branes. So the names comes from the physics interpretation. So yeah, the punchline is that Nakajima and Takayama provided us with these varieties, and we now know how both to study the stable envelopes and the vertex functions, and we can make sense of mirror symmetry and prove it in type A. So what's next? What's next? So in the future, there are many directions to be explored. So surely a very interesting subject is moving from like finite type bow varieties to affine bow varieties. These include extremely interesting examples as the Hilbert scheme of points, or more generally moduli of sheaves on P2 with some trivialization, things like that. Another interesting problem that has not been explored at all, so I will just advertise it, is that to know what happens when one starts introducing non-trivial insertions. Well, actually, there are some special cases where we know what to expect, but for a general insertion, it's not obvious at all what to expect from mirror symmetry. So I guess this is another interesting problem. And well, just to point out that something is super fresh. So there's a new paper by Nakajima. Well, I guess it's been advertised for a while, but now it's on the archive, and it introduces it opens up it's now introduces specific involution on quiver varieties and general on bow varieties that allow to recover, in terms of them, Higgs and Coulomb branches in other types, in classical types, BCD. So it gives a lead on what to do in type BCD. And this is yet another interesting example. And then we will see what else we will be able to do in the future. So I think I'll stop here. Thanks for your attention.
Thank you very much for a beautiful talk.
Thanks.